Good morning. I will speak in French, but my slides are in English. First and foremost, I would like to thank the organizers of ENO Forum. Thank you for giving me the opportunity to transfer oxygen, to speak about oxygen transfer and wine aging and the crucial role of the glass-cork interface. I would like first and foremost to tell you briefly about the place where I work. We are in Dijon, France, as said, and the project is a cooperation between three teams that you see on the slide. ICB, the Laboratoire Interdisciplinaire Chanut de Bourgogne on Material Science, and all absorption phenomena for porous materials. Then we have the Institut Jules Guyot that covers wine science in general. And then my institute, which is about food packaging, and it is a PAM, and this covers also corks. With DIAM, I wrote my dissertation that was presented last year, and now I have a post-PhD contract, and I'm still working on the same topic, which is oxygen transfer. I will try to tell you a bit about the context. You know that very many parameters should be considered with a fairly strong impact on the evolution of wine. Composition being one, which can be more or less sensitive to oxygen, then the position of the storage, which means horizontal or vertical, temperature of storage, the storage time, exposure or non-exposure to light, and additional parameters such as the initial quantity of oxygen in the bottle. These are the various parameters that we can have, and one of the most important parameters is the transfer of oxygen from outside to the inside of the bottle through the stopper. So vis-à-vis the latter, we could investigate and must investigate the role of cork and in general of a stopper for the transfer of oxygen. This is a study that started with a publication in 2019, and we did a case study, studies on 4 bottles of wines. They were selected visually, first and foremost. We saw that in the batch there were 2 bottles with a different color, which meant that there we had an oxidized content. In order to confirm the visual assumption, we performed a series of analyses, first and foremost on the wine and then on the closure. What can we summarize? Well, we performed chemical sensory analysis and metabolic analysis as well. And we indeed realized that in this production batch, coming from two vintages, in 2005, 1 bottle is oxidized and the other is not, and the same goes for 2006. After characterizing wines, we investigated in more depth the closure system in terms of permeability to oxygen. In all cases, there is a higher OTR for the entire system, that is cork and glass, rather than the cork alone. And in the case of the oxidized bottles, there is a higher transfer at the interface. OTR is 1,000 times higher. So evidently, the excess in oxygen accounted for the oxidization phenomenon, and that went through the cork, and especially transfer occurred at the interface between the bottle neck and the cork. As a consequence, we decided to further investigate oxygen transfer mechanisms through the cork and glass bottleneck system. There are four major questions that arise. How can we establish oxygen transfer through the cork? Then, and this is more practical as a question, does the compression of the stopper impact on the oxygen transfer? Third question, what quantity of oxygen can come through the interface? And last question, what is the role of surface treatment for oxygen transfer at the interface? First question, how can we measure the transfer of oxygen through the cork? Here you see what we used. It is a system whereby we follow the development of pressure using a pressure gauge, and you have also a picture of the machine that was used. So we worked also on slides of cork and not on the entire cork only, to reduce the time of investigation with a ring, so to say. The experiment can last days or maximum weeks. You have your sample of cork that you put in between two things, or two sections rather, one with oxygen and the other one, which is C2 on the pictures, with no oxygen, a vacuum. And you see the transfer of oxygen, which is accompanied by a decrease in pressure, because if pressure goes down, then oxygen goes through the cork. So based on the development of pressure, we can also identify a diffusion, scattering or transfer coefficient, which is D on the picture. You can analyze several different samples, which means the cork, and you have the coefficient of the entire cork without considering the interface, or you can analyze and make reference to complex combinations with the cork inside the bottleneck. In order to save time, we used these slides of cork that are sort of wafers. But cork is a natural material. It is heterogeneous, and the coefficient of diffusion for one wafer does not necessarily represent the coefficient for the entire stopper, which is the reason why in the lab we developed an extrapolation model. Starting with and from the experimental distribution of the coefficients for the wafers, we can extrapolate the coefficient of distribution for the entire cork stopper. So we consider our cork as a sort of pile of wafers, whereby we can calculate resistance to transfer in that way. As is the case in an electrical circuit, the resistance of the entire cork derives from adding up the resistances of the wafers. Here we can compare and contrast various samples, even if their thickness changes 3-6 millimeters in any way. We can then add them together and come up with values for the stopper as a whole. Let's now consider the experiment. All measurements were done with the micro-agglomerated corks, where there are particles of cork that are held together by a binder. For oxygen transfer examination, we did the following. First, we calculated OTR for the corks, not under pressure, 24 millimeters, and then pressed ones with the diameter going down to 18.5 millimeters, which is the pressure which is normally applied for corks used for bottles of still wines. We have therefore the coefficient for the cork stopper, and then we consider the OTRs of the cork into the bottleneck in the beginning without surface treatment, and then with the surface treatment with silicone and paraffin. And you can extrapolate values for the entire length of the stopper, which is what you see here. This is for the cork alone. For practical reasons, we made first this analysis. We have the OTR value, which is approximately 0.3. And then we have a distribution which boasts homogeneous values, minimum 0.28 to 0.4. And we have values for the compressed or pressed corks with a slight reduction in OTR, 0.2 milligrams per year, which means that compression performs a moderate effect on OTR, causing a slight reduction. This was for still wines. Second step, we investigated what happens when you measure oxygen transfer in corks without surface treatment. Unsurprisingly, values go up, which means that we have a release of oxygen, and we have 99% of oxygen transfer occurring at the interface. We now apply a surface treatment to the cork before placing it into the bottleneck, and we see that we go back to the initial distribution where we had the cork only, and it is 0.2 milligrams per year. So the coefficient of diffusion of the OTR is similar to the cork alone without considering the interface. So based on the measurement, you see that there is a fundamental role played by surface treatment, which acts as a barrier to oxygen and which makes the closing of the stopper system more tight. To conclude, we focused on surface treatment. We made additional analysis and performed also observations with a scanning electron microscopy. Here you see the surface which is untreated first, whereby you have binders and cork on the surface, and then you have treated surfaces, whereby you see that there is a sort of homogeneous deposit on the, again, surface of the sample that was observed. It is rather thin, because you still see the particles of cork underneath. In addition, we also assessed the thickness of the treatment. the treatment, the film that is created was extremely thin, 1 micrometer. Now, let's try and sum up. What can we learn from these studies? OTR for corks only and still wines. There is a reduced effect of compression on oxygen transfer. Without surface treatment, the system is highly open to the transfer of oxygen, and 90% of the oxygen transfer occurs at the interface. When surface treatment is applied, there is a high barrier effect, which certainly tells us that the surface treatment is useful in helping the cork slide in and out when you cork and uncork, but also performs a role in terms of barrier effect. So the OTR total can be subdivided into 2 components: the OTR of the stopper and the OTR of the interface. And there is a crucial role which is performed by surface treatment. Hence the question, what is the development of the 2 OTRs over the course of time, and especially at the interface? Here you see our literature with several publications, papers that were published on the topic. This is the first case study from 2019, if I'm not mistaken, and then another detailed study on measurement methods. And then there is also a paper on the role of the interface, which was a 2021 publication. Thank you very much for your attention.
Thanks a lot. Now we have Emilie Suhas, who is address us on the OTR measurement using coulometry, the impact of the aromatic composition of Sauvignon Blanc. Good morning, everyone. I'm Emilie Suhas. Thank you for giving me the opportunity to present you the subject, and I would like to thank Julie for giving her presentation. As it's been mentioned, I'm a student of the University of Bordeaux, and I'm in my last year. I'm preparing my thesis supported by DIAM. My thesis will focus on Bordeaux wines, both red and white, so with a long aging over 10 years. I'm going to present the early results of my investigations that concern Sauvignon. To understand the aromatic evolution, as Julie pointed out, the aromatic evolution of wines will depend on a number of factors, inherent factors, as she explained, which are associated with the very composition of wine, the acidity or the phenolic range, and then extrinsic parameters that can affect the chemical reactions in the wine and change its aromatic composition, including the storage temperature or cellaring temperature and the exposure to light. In view of a good quality in evolution, we needed to choose a good quality stopper. The stopper must be inert and needs to display certain mechanical properties. The stopper or closure is where all the gaseous exchanges happen, in particular the exchanges with oxygen, that is the OTR, as Julie said. If you've just walked in this room, the OTR is the amount of oxygen that can get across the stopper, that can seep through the stopper, but also the oxygen that can seep at the interface between the glass and the stopper, and it is important to differentiate this also based on the OIR, the initial oxygen release, which is associated with the compression of the stopper in the first 6 months of storage. In order to measure the OTRs of various closures and old bottles that have aged for over 10 years, it was important to come up with a measurement method that would be appropriate for this approach and this type of samples. We talked about pressure gauging, others use colorimetry. In our study, to study the old bottles, we ended up opting for coulometry. This measurement method does not require any anticipation on the sample. So we can work with bottles that we can get from producers, and we do not need to differentiate the various ways in which oxygen is transferred. The detection threshold is also pretty low, so once we receive the samples, we can dissect the bottles and analyze the stoppers OTR and in the wine that has co-evolved with that stopper. Now, in the course of time, various analyses have helped us characterize different types of closures. We saw that natural corks are the ones that display pretty high variability in closures between less than 0.1 milligrams per year and all the way up to 283 milligrams per year. Other closures display OTRs of less than 20%, synthetic stoppers 1.5 to just below 20 milligrams per year, and microagglomerate stoppers between 0.3 to 8 plus milligrams per year. And then screw caps, which are regarded the ones with the best impermeability, airtightness. Now, it is important to understand how efficient these closures are in modulating the amount of oxygen interacting with the wine. This has an impact on the aromatic evolution of the wines. Now, when wine does not receive enough oxygen, certain notes will develop, which are typically associated to boiled cabbage, and therefore a result of reduction. On the other hand, when you have excessive oxidation, you develop off flavors associated to curry, boiled potatoes, or honey. And it's only when you have a moderate and controlled amount of oxygen that comes into contact with the wine that the wine can express the aromas that are typically linked with the terroir and the cultivar. Therefore, it expresses its full typicality or typicity. When this does not happen, or when we do, when you don't have any reductive or oxidative notes, it's easier to tell the notes that are typical for the cultivar and the terroir and that impart more complexity to the wine. In the course of time, various researchers have studied the sensitive characteristics. In the case of oxidation, you have methanol or phenylacetaldehyde, which are associated with boiled potato or honey notes, while for qualitative evolution or the aging bouquet, you have 3SH or the 4-MSP. 4-MSP, methylsulfonylenone, or 3-sulfonyl-hexanol, which is associated with the quality of Sauvignon Blanc, because these are regarded as varietal thiols. In the course of time, a number of researchers like Joly have first of all characterized the measurement of the OTR to quantify the permeability of the closures. Others have been working on the molecular characterization of fine chemical compounds. Others have worked on the sensory impact of these parameters. Our goal as part of my project was to bring together all these measurements of the OTR after several years of storage and the various molecular markers and their sensory impact. Now, in order to do that, we worked on bottles that had aged, that we sourced. We then cut the neck of the bottle to measure the OTR and the closures. For this methodology, we used a coulometry, which encompasses 3 steps: sample preparation, then sample conditioning to eliminate all the oxygen in the headspace in order to degas the headspace, in order to have stable measurement conditions, and then we went on with the OTR measurement, the OTR assay. So it takes some time to do all of that. After characterizing the OTR of the stoppers, we worked on the molecular characterization, analyzing several parameters such as color, or measuring several markers such as methionine or phenylacetaldehyde associated with oxidation, or 3SH or 4-MSP associated with the varietal profile of Sauvignon, and an evolution in the absence of oxygen. Now, we've used a number of studies to do that. We capitalized on a study DIAM had carried out even before I started writing my thesis on 3 different appellations in the area of Bordeaux, which had been corked in 2008. In these cases, several closures, several stoppers had been used. You see the results here. I wouldn't use time to analyze that in detail, but in general we've used with 2 types of capsules, of caps, Saran and Saranex, 3 microagglomerates with different OTR readings, a synthetic stopper, and then one made of natural cork. We've measured the OTR of these different stoppers after years. And for closures like Saran, I don't know if you see the pointer, the Saran, the DMA, and here's a reversal with those with the picture of the synthetic stopper, and I apologize, but I don't think this is the right slide. Anyway, you see this lack of variability between stopper and stopper. So vice versa, for natural cork, we see that after 2 years of shelf life, you have an important variability among the various corks. So you have OTR readings going from 12 to almost 60 milligrams per year. So a 5-fold factor among the various stoppers. To characterize from a molecular standpoint the various stoppers, we've worked on the first wine. The designation would be Bordeaux, with a natural cork, and we used 13 samples. After 12 years, we measured the OTRs and quantified the markers I mentioned before. To see the various parameters, we carried out a PCR analysis and a PCA, a principal component analysis. And there's over 60% for the horizontal axis, and then you see the readings for the vertical axis, plus 70%. This chart is showing 2 different groups of parameters. On the right hand side you have the parameters associated with oxidation, and on the left hand side you have the parameters associated with the quality of Sauvignon. You also see that the measurement of the OTR after 12 years of storage, of aging, is represented on the same side as the markers associated with wine oxidation. This plot also allows us to generate 3 different groups of samples of stoppers. You see the different colors. There's a group on the right hand side that seems to be associated with oxidation compounds, and another group is on the left. If you look at the OTR readings of these different samples, You will see that the samples that are plotted on the left-hand side have OTR readings which are lower than 2 milligrams per year, while the other groups have readings of more of 2.1 milligrams per year or above, again after 12 years of aging. The two groups are consistent with the studies that had been carried out previously, in particularly a study by Alexandre Ponce in 2021, who proposed a threshold value of around 1.5 milligrams per year, because these wines that underwent an evolution across several years will develop oxidation nodes. We then went on to carry out a statistical analysis. We compared our groups to a group with an OTR of less than 1.5 milligrams per year and one with more than 1.5 milligrams per year of OTR for the various markers. For methanol and acetaldehyde, when permeability to oxygen is low, these molecules are present at concentrations that are close or lower than the threshold, than the detection threshold. When, on the other hand, you are at levels above the perception threshold, the detection threshold, they will contribute to the sensation of oxidative defects, flaws. Now, let's look at the thiols in Sauvignon. The samples that have a low OTR will maintain concentrations of these compounds that are above the detection thresholds. Therefore, in wines with a low OTR, there's a sensory impact also even after 12 years of bottle aging. So, in general, to summarize the results that I have illustrated today, we have several different pieces of information that one needs to remember. The fact that the closures, the stoppers made of natural cork, regardless of the quality, display a very high level of variability between similar corks. We've also showed that the molecular markers that we chose for oxidative variance are correlated with the OTR readings, and then the OTR value higher than 1.2 milligrams per year for the Sauvignon Blancs induces the development of oxidation nodes, and it also is associated with a decrease in varietal thiols. Generally speaking, when you want to age your wines, it is important to use a stopper that has an OTR reading that will be in line with the expected aging, and most importantly, one that is consistent